I mean, the inverse will be very good because they are as independent as possible. And this will be as close to zero as possible. Then our FC, then if we satisfy these two, then this is as small as possible. So that FC will be as small as possible. For FC to be as small as possible means our closed loop eigenvectors will be as independent as possible, and our V1 hat, V2 hat will be as close to zero as possible. Right? Okay. So that our phi bar k and the phi hat k, that equal to V0k bar and V0k hat times ck. Okay, so if that's the case, then if we have, we can then desire, that's our desired eigenvectors, and this is our desired hat, right? Then, if we solve our ck to be, if the ck solved to be, replace this guy to be desired one, right? Then we can solve ck, double ck. So if we solve ck to be like that, so what is our ck? Alright. From here we arrive we know this theory clearly, then you will be able to use this technique for any kind of design you have. Bar V0k hat minus ck. Alright. Now, if I replace this to be my desired one, can I have the desired one? Can I have the desired one equal to that? Now, that's my desired one. Can I have my desired one solve equal to that? Alright. In general, you cannot reach your desired one. But you can approach to your desired one as close as possible by solving the ck in this way. By solving the ck in this way. Alright, that means my ck, if we do that, that means my ck is my head. Alright? My principal, I call principal case eigenvectors will be like this. This is head. Alright? The desired one, we may be able to get it. I can solve my ck so that my real, the feasible eigenvectors as close as possible to the desired one. So this is the vectors are close as possible to the desired ones. In other words, alright, that means what? That means when we solve that, that means my desired k, let me write it clear here. It means bar k, hat k. If I solve this way, that means minus dk hat dk, the norm of that is minimum. Alright? That means that is my as close as possible if I solve the CK this way, the one I just showed you in the page 16. In other words, my VK bar is minus my VK, my VDK bar, and my VK minus my VDK, and take a non-bar like a minimum if I use this CK to do that. That means, alright. So in general, we put this to be 0. Which is never possible to solve it. Unless your open loop eigenvalue are identical to your closed loop eigenvalue, that means you don't need any control. Right? Alright, okay. Alright, now design. This is, I show you some design cross eigenvectors. The identity matrix is one of the design eigenvectors I want to have. Because what? Because that inverse, that matrix inverse equal to identity. Right? That's good. If my design eigenvectors just like this is my first design eigenvector, this is my second design one, and so on. If I have this kind of eigenvectors, then the inverse of that is simple. I don't even need computer to do that. Because that's the identity matrix. Another design eigenvector is open loop eigenvectors. I think your problem number 8 that asks you to have a correct eigenvectors. You know why? Most eigenvectors, open loop eigenvectors are orthogonal. That's why. If you have a damping, you don't have any damping, then your open loop eigenvectors, they are orthogonal. So, that's good, because if they are orthogonal, means that the inverse will be their transpose. Those open loop eigenvalues. Also, we have other orthogonal matrices. The orthogonal matrices means the matrix that we mean orthogonal matrices. Alright? The orthogonal matrix U transpose U transpose equal to U inverse. So, if your orthogonal matrix means my inverse, just simply their transpose. So simple, right? If you have a singularity composition, for example, I have AC, this is n by n, and this is my singularity composition's transpose. If this is real, this will be real, then for that, U transpose equal to identity, and V transpose V is also identity. That means U equal to U transpose equal to U inverse, and V transpose equal to V inverse. So, if I use U to be my desired eigenvectors, then my inverse will be just their transpose. That means very good eigenvectors. But can I reach that? All these three different choices are good choices of desired eigenvectors, but this is not the only three. You can have any others you have. But the three is the one we use in most cases, particularly the second one, open loop eigenvectors. You know why? When you do the Paul placement technique, we remove eigenvalues. Alright, we remove the eigenvalue number below, number called number eigenvalue open loop. We move to number desire eigenvalue. That's open loop. Okay, open. And this is desire cross loop. Cross loop. Now our eigenvectors, are going to any k open loop, any k desire one. Now this is open loop. Then normally we don't want to move our the eigenvectors. We want to keep eigenvector the same.